Hi everyone, welcome to this lecture. In this lecture, we'll be talking about the overview of water resources. Let's get started. So this is a typical water cycle or water resources graph that shows the different inputs and outputs of water resource. So this is an image taken from the USGS, image credit to the USGS, US Geological Survey. And so what it is showing is typically the inflow of water and the outflow of water into the system. So as you can see on the top, the water cycle, water is coming into the system or to the land surface as precipitation. So this is an input parameter in the water cycle. Water is coming as precipitation, it just falls on the ground. It will be as a snow or just a runoff, right? And then, it will be getting into the ground as a stream flow. And some of it is infiltrated, it's called infiltration, and then goes to the groundwater system or the groundwater storage system. And so this is one major way of how water is just entering into the system, right? And then in addition, water is getting out of the system. That means in the water cycle, that's outsourced. So it will be discharged as, for example, evaporation. So if it's a freshwater lake or an ocean, an open water body, water is going out of the system or just discharge it in evaporation. And the other way is transpiration, or you can call it evapotranspiration, in a way that water is gone out of the system, or just that's we're losing water from the system. And then this water is just coming again. It's condensed in the process of condensation. It just gets changed into precipitation, and then that's how it goes and on and on. So precipitation, infiltration, stream flow, and then going into the oceans, evaporation, or just going to plants, roots, and then evapotranspiration, and then just condensation. So that's how the water cycle is underway. So that's a typical water cycle process, okay? And so with respect to fresh water, so there are two major things happening. The first one is, source of fresh water, and then the second one is loss of fresh water. So the first sources of fresh water include precipitation, lakes. These are, sources that we can get fresh water from, and then runoff, especially during a rainfall, and then stream flow, soil moisture on the ground, and also groundwater. And then, ways that we lose water out of the system are evaporation, evapotranspiration, and runoff outflow. So surface freshwater availability is a function of input and output, or just inflow and outflow. Inflow can be precipitation as well as runoff inflow, and outflow can be evaporation, evapotranspiration, runoff outflow, and also infiltration to the groundwater. So this is a typical equation for freshwater, surface freshwater availability. And different sectors have different water resource measurements or parameters. For example, in agriculture and irrigation, we need some water resource parameters to monitor agricultural irrigation. So these include precipitation, soil moisture, and evapotranspiration. So these are key parameters to measure a water resource parameter in agriculture. For example, in drought monitoring, we need to monitor precipitation, we need to monitor runoff, and we need to monitor stream flow, soil moisture, evapotranspiration, and also groundwater. And in reservoir and dam, as part of water resource, these are parameters that we need to measure, right? So reservoir height, precipitation, and runoff and stream flow. So why do we need remote sensing? So we've discussed about various equations of water availability, surface water, and then also different applications or sectors, for example, agriculture and irrigation, and drought monitoring and reservoir and what have you, that we need water resource measurements. But why do we need remote sensing? Why don't we do it a traditional way? Because some water cycle components that we have mentioned before cannot be directly estimated. So these parameters or these water cycle components include, for example, evapotranspiration. We cannot directly measure evapotranspiration, so we need remote sensing, satellites to measure these parameters, or models to combine with satellite data to generate evapotranspiration data, and then runoff data, and also water vapor. So these are measurements or components of the water cycle that we cannot directly measure. So that's why we need Earth observation satellites to monitor and quantify these components or parameters of the water cycle. In this lecture, we'll be talking about Earth observation satellites for water resources. What are the satellite sensors that we use to monitor and quantify different water resource parameters? And we'll be discussing that in the upcoming slides, okay? So this is some operational satellites or Earth observation satellites that we use to monitor data for the land surface as well as the water bodies. For example, here we have GPM, global precipitation measurement, and the SUMI NPP Landsat, the Aqua and Terra, that's the MODIS, and Landsat 7 here, GRACE. So we'll look at some of this, and then this map here. So we'll look at some of the satellites that we need to use for specifically for water resource, right? Okay, so here's a list of satellite sensors and instruments that we need for measurements or quantifying water resource. The first one is Landsat. So Landsat was launched in 1972 and it's still operational. Landsat 8 is still operational. And the other one is rainfall measurement or precipitation measurement. So TRIM, which is Tropical Rainfall Measuring Mission, was launched in November 1997, and which is not operational, stopped operating in April 2015, and it was replaced by GPM, which is the Global Precipitation Measurements, which was launched to replace TRIM in February 2014, and it's still operational until now. And the other satellites are the MODIS Terra and the MODIS Aqua satellites. So the MODIS Terra, these measure water vapor as well as moisture indicator, soil moisture indicator, using various parameters such as vegetation indices such as NDVI and EVI. Okay, so the MODIS Terra was launched in December 1999 and still operational, and the MODIS Aqua was launched a few years after in May 2002, and it's still operational. One of the new satellites is SMAP. SMAP is Soil Moisture Active Passive, which was launched in January 2015, and it's still operational, usually to monitor global soil moisture data. And the last one here in the list is GRACE. GRACE is Gravity Recovery and Climate Experiment, which was launched in March 2002 and still operational. So these are a list of satellites that we'll be discussing in this course, and that we need to use to monitor some water resource parameters. Mind you that there are other satellites that we're not covering in the scope of this course, but these are the major satellites that we will be using in this course to demonstrate how we can apply remote sensing for water resource applications. Okay. And again, I've said this in the previous lecture, but I just want to reiterate this. So why do we need remote sensing for water resource application? Why don't we just go ahead to the field and measure some of these parameters? The reason is that some water cycle components cannot be directly estimated. Some of these include evapotranspiration, runoff, water, vapor. So to measure these parameters, we need to indirectly, use remote sensing or satellite data, and then just quantify them using, proxy proxy or surrogate measurements, or some other model estimates, to calculate these components of the water cycle. Okay. And which satellites measure what? So, to kind of categorize. So we can use Landsat satellite to measure evapotranspiration, okay? And also, we can use MODIS to measure evapotranspiration, but because Landsat is a 30 meter, pretty high resolution, the ET or evapotranspiration from Landsat would be more robust. And in terms of precipitation, if it's historical precipitation, we can use TRIM. And if it's more recent, data, we can use GPM. For MODIS, obviously, or evapotranspiration and, VI indexes, NDVI and EVI, we can use, the MODIS instrument. And SMAP is used to monitor, just quantify soil moisture. And the last one is GRACE. We use GRACE to quantify groundwater storage. And then we'll use, these satellites in our examples and, exercises in the course. Okay, what are the advantages of satellites for water resources? So the first thing is global coverage, compared to surface or station-based point measurements. In addition, estimates are available where station or surface-based measurements are not available. That means places that are not accessible, you can estimate them using satellite data. And then most importantly, satellite data are freely available for public. That's amazing. You can get satellite data for over decades and also covering the entire planet. That's incredible. And the last thing is, the Earth system models integrate, point or station-based and satellite observations to generate models that can be used in various, applications. So in this lecture, we'll be talking about how Landsat is, used for water resource application. So just give you a little bit background about the Landsat satellite, okay? So Landsat has been launched in 1972. The first Landsat satellite was called Landsat 1, and it operated until 1978. And then the second, Landsat 2, was launched in 1975, and it extended until 1982. And Landsat 3 was launched in 1978, and it stayed until 1983. And in 1982, Landsat 4 was launched, and it stopped operation in 1993. And Landsat 5, it started operation or just was launched in 1984, and it stopped operation in 2011. That means 2011. Okay, and then Landsat 6 was launched and stopped in the same year, so it was not successful. So 1993. And Landsat 7 still operational, starting from 1999. The more recent Landsat satellite was Landsat 8, so it was launched in 2013, and it's still operational. So Landsat technically has 4 decades of Earth observation data to monitor our planet. So these are satellites about 30-meter range, and then some bands 15, some bands 60-meter. But on average, most of the Landsat bands are 30-meter spatial resolution. So it just we get data every 16 data. That means every 2 weeks we get data for the entire planet. Okay. So as I mentioned, there are Landsat sensors from 1 up to 8. The only unsuccessful launch was Landsat 6. It started from 1972. So Landsat 8, was launched. The more recent one in 2030 is the newest sensor in the program, and capturing between 550 to 750 nanometer new image. We can say every day, but it's just 16-day for most of the Landsat sensors. Okay. This is how the Landsat satellite looks like. This is a NASA image. Credit to NASA. This is how the Landsat satellite is while observing the Earth's surface. So just to give you an idea of how the Landsat satellite looks like. And some details about the different Landsat sensors. So Landsat 1, obviously I mentioned the date range, but it has multispectral scanner, and its spatial resolution is 60 meter. And Landsat 2, the same instrument, multispectral scanner, 60 meter, spatial resolution. Landsat 3, MSS, 60 meter. And Landsat 4 has 2 instruments. The first one is multispectral scanner, and the second one is thematic mapper. And it has 60 meter for the multispectral scanner and 30 meter for the thematic mapper. And Landsat 5 had the same 2 instruments, multispectral scanner and thematic mapper. Both of them are 30-meter resolution. Okay. And then Landsat 7 is still operational, and it has an advanced instrument which is called ETM Plus, which is Enhanced Thematic Mapper. So we have most of the multispectral bands. We have 30-meter spatial resolution, and the panchromatic is 15 meter. And Landsat 8, which is an exciting one, was launched in 2013, has 2 instruments. The first one is OLI, and the other one is TIRS. The first one is for the optical, instrument. The other one is the thermal. Okay, and they have 30 meter and then 15 meter. The 30 meter is just a multispectral, and the 15 meter is the panchromatic band. This is how a Landsat time series image looks like for the United States, just to give you an idea of how Landsat satellite image in time. In this lecture, we'll be talking about the MODIS instrument, which has the Terra and the Aqua satellites. So, what is MODIS? MODIS is a moderate resolution imaging spectroradiometer. That's MODIS. It has 2 satellites on board. So the first is the Terra and the second is the Aqua. So the Terra has an equator overpass of a 10:30 a.m., whereas the Aqua satellite has a 1:30 p.m. equator overpass. And so the Terra MODIS and the Aqua MODIS are viewing the entire Earth surface every 1 to 2 days, right? It has the MODIS instrument also has 36 spectral bands. That's a lot of bands, and it comes with 3 spatial resolutions. The first is 250, and the medium is 500 meter, and the third one is 1,000 meters, 1 kilometer spatial resolution. Okay, and so that's how the MODIS captures an image of the entire planet. And there are different products that we get from the MODIS instrument, especially for water resources. So the first one is vegetation indices. What vegetation indices do we get? the normalized difference vegetation index (NDVI), which is a popular one, and the enhanced vegetation index (NDVI) or EVI, sorry. So these are indices that can help us monitor the health of a vegetation, right? And another other inputs that we get, or just products that we get from the MODIS instrument, are NDWI, which is a water measurement index, which is normalized difference water index, NDWI. Okay, and the other parameter is evapotranspiration. So we can get a MODIS based ET, evapotranspiration product. These are some of the parameters, or just measurements that we can get from MODIS, especially with respect to water resource. We can also get land surface temperature, not necessarily directly useful for water resource, but that's a parameter that we get from MODIS. Okay, so this is how the MODIS from NASA, how this is a time series of monthly vegetation index, NDVI, of the MODIS for the entire planet. You can see how we can monitor our planet using satellite data, the life of our planet technically. If you see the green areas here, and in the Amazon and the Congo basin and the Sahara Desert here, so you can monitor or quantify the land surface covering the entire planet, and also spanning over decades. That's amazing. And so this is a typical MODIS image. This is from the Terra satellite, actually. And so this is an example of a raw image with without cloud masking or anything. It's just a raw image of a MODIS Terra satellite. This lecture talks about TRMM and GPM, two satellite instruments that measure rainfall. The first one, TRMM, has stopped operation, and the second one, GPM, has been recently launched and replaces TRMM. So, TRMM, what is TRMM? So TRMM is a tropical rainfall measuring mission, an acronym which is a joint mission by NASA and the JAXA, the Japanese version of NASA, since 1997. They provide data on a daily temporal resolution. That means 3 hourly. It also covers. It has a global coverage. That means it extends from 50 degree south to 50 degree north latitude. And it has a spatial resolution of 25 kilometer. So that means a single pixel, TRMM pixel, is 25 kilometer by 25 kilometer. Okay, and it has 3 instruments. The first one is TRMM microwave imager, TMI, and the second one is precipitation radar, PR, and the third one is VIRS, visible and infrared scanner. So overall, that's some background information about the TRMM mission. So this is a TRMM data, a global data by NASA, which shows global coverage, but also temporally monthly data, from 1999. So you can see how it's very helpful to use satellite data to monitor precipitation or climate. There are, for example, places that we cannot access, or there are places that we don't have meteorological, ground stations. So by using satellite data, we can get a global wall-to-wall coverage, and also decades of time series. That's an amazing data source. The second is GPM. So GPM is a global precipitation mission to measure rainfall. So the GPM Core Observatory is a consortium of partners in the United States, Japan, France, India, and Europe. So the GPM observer observes precipitation over the entire planet every 2 to 3 hours. It has the same spatial resolution, 25 kilometer, and then the core satellite will measure rain and snow. And then there are two instruments, the GMI and the DPR. The GMI is the GPM microwave imager, and the DPR is the dual frequency precipitation radar. And the GPM covers more areas, which means by extending trim to 65 north and south, and that's an extended coverage, especially in the temperate areas. And GPM, has some advantage compared to trim, because GPM, I think GPM is designed to measure light rain and falling snow. So it's a significant water resource, measurement, especially inflow, especially in the high latitudes, right? So the GPM instrument extends the capability of the trim sensor to detect, falling snow, and it also measures light rain, actual rain. Okay. In this lecture, we'll be talking about SMAP, a new satellite that will monitor soil moisture for the entire planet. So what is SMAP? SMAP is a soil moisture active passive satellite, and it provides a capability for global mapping of soil moisture with an enhanced accuracy and temporal resolution, or just the frequency of data. So the mission acquires this measurement for at least 3 years with global coverage. So spatial resolution currently ranges from 1 to 47 kilometer, and it provides global coverage within every 3 days at the equator, and then every 2 days at the boreal latitude. That means greater than 45 degree latitude or just north. So potentially SMAP data, or the soil moisture data, is very useful for applications ranging from weather forecasting, drought monitoring, flood and landslide, agricultural productivity, human health, and water resource, which in this case we are interested in, right? So this is an example of SMAP data, a soil moisture data at a global level, generated by NASA at the Jet Propulsion Lab in California. So this is how we are able to quantify soil moisture using the SMAP data. Soil moisture is obviously one important parameter in the water cycle, so it's very useful to get this data. So in this lecture, we'll be talking about GRIS, a satellite that measures the water storage. So we'll provide you some details about that. So it's a sun-synchronous orbit, and there are two or twin satellite system, and it covers the entire globe. And the spatial resolution is pretty low. That means it's a pretty coarse spatial resolution from 300 to 400 kilometer. And the temporal coverage is it started in 2000 to March 17, and it's operational until now. And temporal resolution 250 gravity profile per day. So that's a typical observation from GRIS. So the thing is, it's a gravitation field measurement. But what happens is that when there's movement of water in a certain place, then that gravity changes. So, and then by way of measuring the change in water storage in an area, we can quantify, the spatial temporal dynamics of water in that area, or just the presence of water in that area for a certain period of time. And then that tells us about drought, that tells us about water availability in the soil or the groundwater. So that's a pretty good indicator of water resource parameter. And one of the things that we can use GRESS data is that we can, it's a month, like it's a monthly data. So, and we can map, for each month, and then we can subtract with the long-term average, and then we can get like change. That means anomaly for each month. What is it increasing or decreasing trend of water storage in that area? That tells us a lot about groundwater storage, or soil moisture and what have you. Let's dive into Google Earth Engine. First, let's explore the main website. Here's the Google Earth Engine website. Once you type in earthengine.google.com here, you'll get to the main Google Earth Engine website. And then you have explainer video by Google and a planetary scale platform for earth science data and analysis. You can also watch the video if you're interested. Pretty nice explanatory video about Google Earth Engine. If you're new to Google Earth Engine or geospatial data analysis on the cloud, this is kind of a nice time well spent on this video. But if you want to skip that, you can skip, and let's go to the other parts of the website. And there's an explanatory conceptual model, a satellite imagery, an algorithm, and a real-world application. That's kind of to explain conceptually what Google Earth does. Global scale insight on data on a time series basis, and some sample screenshot of the code editor on Google Earth Engine, significant humanitarian impact application of Google Earth. This is the main website. And the first thing that I would like to explain is the time lapse on Google Earth Engine. This is technically a large volume of data since 1984 to 2016, organized in a way that explains change over time. What the time lapse does is, for any part of the globe, any place on the planet Earth, you can select a place, and then it shows you annual change over time starting from 1984 to 2016 using a true color composite satellite image of the Landsat to 30 meter spatial resolution. If I, for example, use one of the time lapse already done, for example, here Las Vegas, you can understand the change, how Las Vegas has expanded or dynamically shown growth from 1984 to 2016. You can see that clearly on the satellite image, dynamically, how it expanded from time to time. You can see that the city is just expanding, growing from 1984 to 2016. So this is, the time lapse. You can choose any, you can type in any place on Earth, and it will show you that change visually. That's a pretty cool application, right? The second thing that I would like to show you on the main Earth Engine website is a datasets. If you click the datasets part, these are the list of datasets that Earth Engine archives. It ranges, imagery, geospatial data, climate and weather, and demography. If you look at the imagery, they're sorted by satellites. The Landsat satellite, for example, if you click this link, it will take you to the data catalog, and the Sentinel satellite, a MODIS instrument, and some other high resolution imagery, and a nighttime light sample. So these are just sample satellite data, but if you click to one of these, it will take you to the main Earth Engine data archive or data library. And here you have geophysical data, including topographic or terrain data, land cover data, agriculture or crop data, and also land surface temperature from various sensors, including MODIS, ASTER, and AVHR, and other geospatial data. And in addition to this, you have a list of climate and weather data, and this is weather data from the TRMM, rainfall, tropical rainfall, precipitation measuring mission, which is actually data replaced by GPM, global precipitation measuring mission, and then some other climate data on Earth Engine. And the last bit of data that you have access on Earth Engine includes some humanitarian or demographic data, including the world pop, which is a population density at a global level, and also some public health data, malaria here as an example. So these are the list of data that Earth Engine archives. So if I click one of the satellite images, for example, it will take me to the main Google Earth Engine list of a library of data archive, as you can see here. If you tag, like, for example, Landsat, you can see 196 rasters, ranging from Landsat, the first Landsat missions to the current Landsat. But if I define here, for example, Landsat 8 data, the search will kind of focus and the list will be minimal. And for example, you can choose any type of data that's available on Earth Engine. Here, SRTM, that means digital elevation model. You have 24 different rasters that show you elevation or topography. So this is how you can access data on Earth Engine. Once you have accessed data, you can either visualize this on the workspace. If you click here, it will show, or you can also access them programmatically by using on a JavaScript or a Python script. So using an Earth Engine API, you can access by writing code. So for example, here, let's open one of the data here. And then here's the list of data and then some metadata information. Open in workspace, and I can open that and then click apply. And so the elevation data global level will open for me. So that's kind of how you access data on Earth Engine manual. You can also download such data using workspace, or in a later lecture, I'll show you how to programmatically using script, a computer code to access data on Earth Engine. So now let's go back to the main Earth Engine website and show you some other features on Earth Engine. You can also, on the main website, you can also access some case studies. These are case studies that applied Google Earth Engine as a geospatial cloud platform, geospatial data analysis cloud platform. This is a popular one, a global forest cover by Matt Hansen, showing forest cover at a planetary scale at a 30-meter resolution, starting from 2000. And map of life. This is an interactive map for biodiversity and conservation, and global forest watch. Another extended application by Matt Hansen. So there are various platforms on Earth Engine: a code editor and Explorer. The code editor is where you can access data by using scripts or code, and the Explorer is the one I've shown you earlier. You can manually use a GUI, graphic user interface, to access data on Earth Engine. In this lecture, we'll talk about code editor on Earth Engine. Let's dive in. To access the code editor, I'll go to platform and click code editor. Then it will take me to the code editor page, main page. Okay, so let's start. An code editor is an API, application programming interface, that you can access Earth Engine library of data, planetary scale geospatial data on the cloud using JavaScript and also Python script. So let's look at each part of a code editor. So the first part is the code editor editing section. So here in the code editor, you can write script and print or just get info and also map and export. You can do various applications using the code editor. As an example, let's print our first programming script. Let's print hello world. Print, it's a string, so I'll put it in a quote, hello world. And in a JavaScript, to close a statement, you have to use a semicolon. And if I run that, it would show on the console output. So that's effectively we're writing our first JavaScript programming language on code editor. And this is on the right side, you find 3 pieces of buttons. So the first one is inspector. So the inspector helps you to inspect location, pixel values, objects added to the map, and other elements. When you click here, it will show you those layers or elements or maps, and then their information associated with each point. If you move to from different places, for example, since we don't have any layer on the layer manager, it will just be only the lat long information, right? So it will just tell you the latitude and longitude of that point. So that's how you use the inspector, button. And the second one is the console. It's called console output. So it will provide you, for example, here we wrote a script, print hello world. If I print that, and I have an output, hello world, a print. So it's just a console output where you can print your error message and some progress information and things like that. And the last bit here is task manager. So the task manager will help you to monitor some progressing activity. For example, if you export your data here, you can run the export and also monitor the progress. If it's complete, it says complete. If it's progress, it will show you the time that it lapsed to complete. And that's in terms of what you have on the right side of the code editor. And here you have a layer manager, which is not showing here, but it will show if I have something to print here. And the map in the satellite view, you can toggle between the two, the map view and the satellite view. So this is the satellite image. If you zoom in, it can take you at a pretty high res, and you can access the satellite image of each point on any place on Earth. If you're interested on the regular map, then you can go back and forth with the satellite image and the map. Okay, and as I mentioned, here is the map, the code editor, and then here's at the bottom is the map where you can visualize your analysis output or just product. And on the left side here, there's a zoom button. You can minimize and zoom in, and then zoom out if you want. You can change the satellite image, so it will help you to zoom in, zoom out. And this is a geometry tool where you can effectively digitize or create features, including point, line, and polygon. So if you click one of these, for example here, and you can digitize or create a polygon by using this feature, right? and it will automatically create, you know, geometries or just points here. So I would exit for now. I don't need this, just for a demonstration purpose. And okay, I can delete this. Yes. Okay. The other important feature on Earth Engine is the script manager, where you can create a script and create a folder, and even you know, save your script. Here, for example, this is I can open this script. So this is a script you know, already saved here. So you can save your script. You can share your script with collaborators. And here's the API documentation. You can access some algorithms and then some example scripts if you're interested in. The third one is the assets. You need the asset manager, where you can import data to Earth Engine, and you can access it using an asset ID. And here's a get link button. The get link button, for example, for this script, if I wanted to share it with other people, I would generate a get link, and then it would automatically generate a link. So I can copy that link and then share it with other people. So when they open it, they'll have the same script. They'll access the same script that I'm opening here. And the save script is every time you create, modify or edit your script, you are able to save it or save as. So it will help you, archive your script as you progress on your work on Earth Engine Code Editor. And you can also, once you have your script written, you can run the script, and if you have an export, you can run it here. If you have some visualization, it will show up here. So this is where you run your script from the code editor. And there's also some help menu where you can access some tools and guidelines. So overall, this is how the code editor looks like. You have a script manager, API documentation, asset manager, and the code editor where you write a script, and then the map, and then the zoom and the geometry tool where you create features. You can toggle between the map and the satellite image, and here the inspector, and then console and task manager, and some help. In this lecture, we'll be talking about mapping surface water availability using Landsat data, okay? So let's get started. So the first thing, as always, is I would like to import or just create a steady area or region of interest, or whatever you call it, just to focus our analysis. And then I'll just create this rectangle, give it 4 corners technically, and just let's try to map it so that we'll see where we are. Okay, so this is technically the source of the Blue Nile River, which is a famous river, and the Nile Delta here just goes all the way here to the Mediterranean Sea. So we're just here at the source of the Blue Nile River in Lake Tana, in the highlands of Ethiopia. Okay, so this is our study region for this analysis. So the next step is to import water data. So here we're not directly using Landsat data to analyze or map surface water availability. So this GRC global surface water data is already available, and which is a research result, and in that paper, just in that data product, we can get occurrence of water, just presence of water for the entire 1984 to 2015. That's a long time series. So we'll be using this data and just explore how we can map surface water body availability using this data. Okay, And so so what we're doing here is just I'll declare a variable water and then create image and import the image ID. This is the image ID for this water data. And in this data, we can call different variables. So in this case, I'll just call occurrence of water, so which is stored in the variable occurrence. So I'll call it water occurrence. You can name it differently, and then just call this water data and select this variable like occurrence, which tells us how and where surface water has occurred over the past few decades, right? And let's map that actually. So what it tells us is just single color for water occurrence, whether there's water or there's no water in that area for that entire period. Okay, so let's map that. Okay, so it's just technically what it tells you is just over that span of period, like 1984 to 2015, if on this place there was water or just the presence of water, and you can see that. I mean, the image is for the entire globe. You can see that for an entire South Sudan here, just the Nile delta. You can go here, the Nile basin here, White Nile here, and then just the Nile delta. All right. So okay, let's zoom out here. Okay, just want to show you the Nile delta. All right, Nile delta, zoom in. Okay, here you go. Yeah, you can see the Nile delta here. Pretty much inundated. Okay, so let's just focus to our study. All right. So what it tells us is that we can also use the zoom in, zoom out, button here. So what it is telling us is that just the presence of water in absence. All right. So that's pretty useful. We can use these for different water resource applications, right? And this is not like a single time, but this is just over an entire long time periods starting from 1984, right? But we can also just get more information from this. That means the frequency of occurrence of water in this area. Is it like a short time period, like only in a certain year, or just for the entire year? Is it a perennial, a permanent water body, or is just temporary water pools that are created due to like rainfall or temporary situations like flooding or what have you, right? So the next analysis will give us that, right? Okay, so the next step is just to create a map that so what we can do here is technically just we will map the occurrence map based on frequency, right? So higher frequency will have like closer to 100, and then zero, or the no water, just closer to 0. Okay, so that way, and then also we can color code it, just green, yellow, red. That means green is like the highest frequency of water in that area, and yellow is the moderate frequency, and then red is just there was literally no water or just closer to no, right? So this is our visualization parameter for Viswater, I'll call it here, Viswater, okay? And then water occurrence, update mask water occurrence. So it will just only give us data for this water occurrence, and then just color code it. So let's map that. I think that should be ready to go. So that means water occurrence changed from 1984 to 2015. Almost 20, that's like 30-year period, right? That's a long, time series. All right, okay. Fantastic. So let's just get rid of that. And okay, so now what we have instead is we have this water occurrence map showing us that by giving us different color code. Let's just zoom in, use the zoom level. Okay, so what we have here is that, you know, if it's green, closer to 100, we'll have water occurrence for an entire period, like for the entire period. So that means this is a big lake. There was just literally water almost all the time, right? And whereas if you look at these areas, like you can see the satellite image actually. And then if you look at this, the sky here, it's just red, right? The reason is because when there's like higher, you know, rainfall or just flooding, this area will be having water, but it's just inundated flood water. It's not like a water body. But when there's high flooding, or just when the water is, you know, overflowing, this area will be, you know, inundated. So it tells us that there's the occurrence, there's less occurrence of water in this area compared to here. So we can see that there was some water sometime in the past, but it was not like all the time. So that's how we can, you know, interpret our water occurrence map, which is very useful. Another example is that, you know, this is Olga Dam. It's a big dam. If you look at it, just zoom in here, you can see that it's red because this dam was, you know, constructed nearly like 15 years before. So there was not water during the entire period. So water was just only some part of, you know, this period. So that's why it's just yellow reddish, right? So that's a very good, you know, indicator to understand the dynamics of water over time, right? At a global scale. That's amazing. And just to be able to map, you know, presence of water for the entire planet for nearly 30 years is incredible. This is the power of, you know, big geospatial data to understand change over our planet. So that's how you can use the already processed, you know, GSW, you know, water from GRC, which is a research paper published, and the product is, you know, available for public use. So this is an important piece of work derived from actually the Landsat sensor. So you can use it for different water resource applications in your study area. In this lecture, we'll look at how you can map soil moisture data from this map sensor. Let's get started. The first thing is, as always, I would like to import a feature collection for our study area for this analysis. So I'll import the global admin area for all countries. It's a fusion table, FT. I will provide that fusion table ID, and then I'll name it world. You can change it. You can change the name if you want to. And then the next step is to import the image collection from our Zinj library. I'll name it SMAP as a variable. And by using EE image collection algorithm on Earth Engine and providing the image collection ID here, and I'll do a few other filters. The first is I'll filter the image collection by date. So my image will only be covering 2015, starting from 2015 January to ending 2017 December. And the other thing is, since this image collection contains other parameters, I'll only select SSM, that means soil moisture data. And also I'll apply filter bounds to only give me data that overlays on with this study region. So and so this is what I have here is just imported an image collection spanning from 2015 to 2017. But if you want to display the an image here, it's better to have a single year, right? So let's create another filter, another variable, which is SMAP 2017, and then use the already created image collection, which is this map here that contains data from 2015 to 2017, and just filter, apply a filter by date to only select 2017 data. As you can see here, we have January 2017 to December 2017. So we're calling this image collection already created as map here, and then filter by date, so that will only have data for the year 2017. Again, I'll just select SSM to select that variable, and a median value. So the reason I need a median value is just I'll aggregate, since this is a lot of data, I'll aggregate the entire image collection and just create one single image. That how that is applied or processed is that by calculating the median statistics, the median pixel value for all the images in this image collection. Okay, so the next step is to create a visualization parameter. I'll name it SMAP Vs, just defining a minimum and maximum values for, and also different color combination for that plotting. Okay, so the last thing is just to display the actual map. So here, as we said, we'll map this 2017 aggregated composite median value for the year 2017, so that what it gives us is a soil moisture for our study area, and a median soil moisture for the entire 2017, right? And then I'll clip it by study area and then import the visualization parameter here. I'll name it SMAP 2017, and as always, I like to adjust the zooming or just the focus of my map display by calling map.center object, and let's run that. Excellent. So this is our soil moisture for 2017. So this is a median soil moisture value for the year 2017. Okay, it's a global data. So what we have here is that the blue areas are low soil moisture, and whereas the red and the yellow have higher soil moisture, right? If you look at the Congo Basin here, you have a pretty good higher soil moisture. If you look at the Sahara Desert, pretty much low soil moisture. That kind of makes sense. So this is just an example of how you can plot SMAP data on Earth Engine.